Hi, this is Seth, and I'm making a Stat 110 bits video about Markov chains. Specifically, we're going to look at the two-state Markov chain with the transition matrix Q here, and then we're going to answer these three questions about it. So there are kind of two types of Markov chain problems that you're most commonly going to get. One is when you're given like a bubble diagram like here, and then you're supposed to like figure out transition probabilities from that. And another type is here, where you're given a transition matrix, and you're asked to solve a problem about the Markov chain that transition matrix represents. And the thing that I like to do in these type of problems is to draw a picture, because pictures always help me visualize what's going on in the problem. So remember that in a transition matrix, we're going from the rows to the columns, and that's our convention in the class. And we also use row vectors. And so what the transition matrix is telling us is, one, that we have two states, which is given to us in the problem, and by the fact that Q is 2 by 2. And then it's saying that we're going from state 1 to state 1. And if we do that, that has probability 1 minus alpha. So from 1, you go back to 1 with probability 1 minus alpha. And you go from 1 to 2 with probability alpha. And it's the same thing for the second row. We go from 2 to 1 with probability beta. And we go from 2 back to itself with probability 1 minus beta. Okay, so the first question is asking us to find an alpha and a beta such that the chain is reducible. Now, reducibility means that if you have a state I and j, the chain is reducible if it's impossible to go from I to j in a finite number of steps, or from j to I in a finite number of steps. Cool. So one way to do that is by setting, by like breaking these links here. If you break these links, then what you're going to have is like 1, 2, and it goes here with probability 1, and it goes here with probability 1. Because that means that once you're at 1, you just have to keep going back to 1, and there's no way that you can get to 2 in a finite number of steps. And vice versa, if you're at 2, you're just going to keep going in a circle here at 2, and there's no way for you to get to 1 in a finite number of steps. So one way to solve this problem is just to set alpha equal to 0 and beta equal to 0, because that essentially, it breaks these links. So this problem was solved basically just by understanding what the definition of reducibility is. It's, if you're at state I, you can't get to state j in a finite number of steps. And if that is true, then the chain is reducible. Great. I hope I was saying reducible and not reversible that whole time, because I was talking about reducibility. All right. So let's assume that alpha plus beta is not equal to 0. We need to find the stationary distribution. So I'm going to get rid of these. And we have alpha plus beta is not equal to 0. And I want to find S. Cool. So if we know that S is stationary, we know that by definition SQ is equal to S. So S must be, two-dimensional. So if I write down S1 and S2, and I have Q, which is 1 minus alpha, alpha, beta, 1 minus beta, then this must equal S1 and S2, because I know that this equation holds. I also know that S is a distribution, which means that S1 plus S2 is equal to 1, with S1 and S2 both greater than or equal to 0. Right? They're probabilities, so they can't be negative, and they must sum to 1. They also can't be greater than 1, right? They're probabilities. And so what I have is a system of equations, where the first equation is this guy, and the second equation comes from this matrix multiplication. If I do this matrix multiplication here, I have S1, 1 minus alpha, plus S2 beta is equal to S1. And I also have, if I do this multiplication here, I have S1 alpha plus S2 1 minus beta. That's equal to S2. Now I have these three equations, and from here I can basically solve the problem just by solving this system of equations. So from this, I know that you can rewrite this as S1 minus alpha S1 plus S2 beta is equal to S1. I subtract S1 from both sides, and I get that 0 is equal to negative alpha S1 plus S2 beta. I add alpha S1 to both sides, and I get S1 alpha is equal to S2 beta, and then I have S2 beta over alpha is equal to S1, and I've solved for S1. Okay, great. Now I'm going to plug this back into equation 1. So I know that this is true, but I also have an equation for S1 in terms of S2, so I'm going to plug that in here. So this is actually S2 beta over alpha plus S2 is equal to 1. Now I have an equation where the only unknown is S2, and I can solve. So this is S2 1 plus beta over alpha equals 1. So S2 equals 1 over, I'm going to write this 1 as alpha over alpha, which means that this is alpha plus beta over alpha, which is equal to alpha over alpha plus beta. Great. Cool. And then I can use equation 1 again, because I have S1 plus alpha plus beta is equal to 1, which means that S1 is equal to beta over alpha plus beta, which means that S is equal to beta over alpha plus beta and alpha over alpha plus beta. Great. And that's the answer. That's a stationary distribution. Okay, cool. Now that third question is asking us, is this chain reversible? So I know if I can show reversibility with respect to some vector S, that implies that S is stationary. So when I'm trying to show reversibility and I already know what the stationary distribution is, I want to show reversibility with respect to that stationary distribution. So what I need to show in order to show reversibility are the detailed balance equations, which is that the following is true for all I and j. Which means that I really have two cases that I want to consider. One is when I and j are equal to each other, and then one is when I is not equal to j. Well, if I and j are equal to each other, this becomes a silly exercise, because that's saying that this is true, which, yeah, I just don't have anything else to say about that. That is, if you write the same thing on both sides of an equal sign, that is true. So really, the interesting things are I not equal to j, but since we have only two states, we only need to consider, when I is equal to 1 and j is equal to 2. And, we'll only do this once, and we're not losing any generality here. We could equally pick 1 equal to j and I equal to 2, but, yeah. So, S1, Q1, 2, and we hope that this is equal to S2, Q2, 1. Okay? And we're using this stationary distribution S here. So S1 is beta alpha plus beta. And what is Q12? If we go back to Q12 is right there. It's equal to alpha. So this is beta over alpha plus beta times alpha. Okay, what is S2? Well, from our previous part, we know that S2 is alpha over alpha plus beta. And then what is Q21? Q21 is beta. So this is times beta. And lo and behold, these two are equal to each other. And so we've shown the detailed balance equations for all I and j. So reversible is a check. Great. So yeah, I hope that was helpful, and I'm happy studying.